welcome to Next Gen Manufacturing Nexus. Today, we're diving deep into the world of aerospace manufacturing, and specifically, the one thing that holds it all together, an absolutely unbreakable chain of quality control. Let's jump right in.
You know, this quote right here, it just nails it. When you're dealing with millions of parts that all have to work together perfectly, good enough is a recipe for disaster. The real standard isn't just excellence, it's perfection, every single time.
All right, so here's our flight plan. First, we'll talk about why the stakes are so ridiculously high. Then we'll peek inside the rulebook that guys like Boeing use. We'll follow what happens when something actually goes wrong, look at the tools they use to learn from it, see how tech is changing everything, and finally, check out the massive payoff for all this hard work.
So what's the one word that drives this entire system? The one thing that keeps engineers up at night? Let's break it down.
It's called a nonconformance, and really it's any time a part or even a process strays from the original blueprint. We could be talking about a microscopic crack in a turbine blade, the wrong chemical mix in an alloy, or even a single missed step in a huge assembly line. Any deviation, no matter how tiny it might seem, is a big deal.
And this is why. A tiny, almost invisible flaw in one little component can kick off a catastrophic chain reaction. Seriously, in aerospace, there are just no small mistakes. The stakes are way too high for anything less than absolute precision.
So, to stop these deviations before they even start, manufacturers don't just, hope for the best. They build a fortress of rules. And to see how it works, let's take a look at one of the biggest players out there, Boeing.
Now, this is not just some simple checklist. We're talking about documents with thousands of super specific rules, called QRs. And every single supplier, from the company making tiny bolts to the one building massive engines, has to follow this rulebook to the letter. It's the absolute bedrock of their quality system.
And what's so fascinating is the incredible level of detail here. It's not just, hey, use the right metal. The rules get super specific, explicitly forbidding things like changing the heat treatment of a material or trying to hide where a part came from. They even make suppliers report the findings from their own quality audits. Every link in that supply chain has to be completely transparent and totally verified.
So what happens if a supplier does break a rule? Well, the consequences are immediate, and they're expensive. Just look at this table of automatic charges. The administrative fee alone can be $1,000. And that's before you even get to the cost of fixing the mistake. The takeaway is crystal clear. Quality isn't just a goal, it's a binding financial contract.
Okay, but let's be real. Even with the world's best rulebook, things can happen. What's absolutely critical is having a systematic, step-by-step playbook for dealing with it. This is how you build a reliable path from defect to fix.
This is that standard playbook. And notice, it's not a panicked scramble. It's a calm, methodical process. The second a defect is spotted, it gets plugged into this structured workflow. Every single stage, from inspection to repair, and maybe most importantly, documentation, is meticulously controlled. There is absolutely no room for guesswork.
But here's the thing. Just fixing the broken part? That's not good enough. The real goal is to make sure it never, ever happens again. And that requires some serious detective work.
This is where that detective work starts. It's called root cause analysis, or RCA. And it isn't about blaming a person or a single machine. It's about asking why over and over again, digging past the obvious symptoms to find the fundamental flaw in the system that let the failure happen in the first place. And engineers have a whole toolkit for this. Take a fishbone diagram, for example. It helps them map out every possible cause you can think of, from machinery and materials to methods and manpower, and see how it all connects. Combine that with something like the 5 whys, and you've got a multi-pronged attack to hunt down the true source of the problem.
Now, all these processes, these ideas, they've been around for decades. But right now, technology is coming in and supercharging every single step.
I mean, just look at this comparison. We're moving away from mountains of paper and manual checklists to a fully digital workflow. And the huge shift here is going from focusing on individual little steps to seeing the entire process chain at once. This lets engineers spot patterns and potential problems in a way that was literally impossible with old paper systems.
And these are the game-changing technologies making it all happen. You've got AI and machine learning that can sift through unbelievable amounts of data to predict failures before they even occur, And digital twins. We're talking exact virtual copies of a real part. Allow engineers to run stress tests in a simulated world, perfecting a fix without ever touching the factory floor. This isn't science fiction anymore. This is the new reality of manufacturing.
So, what's the result of all this investment, all these rules, all this incredible technology? Well, the payoff is just staggering.
First up, speed. By catching errors early and digitizing the entire response, manufacturers can actually triple their production throughput. Why? Because getting it right the first time is always faster.
Next up, money. The cost of poor quality, things like scrap, rework, delays, it's a massive expense. A really solid digital system can save a major aerospace company $10 million a year.
And finally, we have efficiency. By managing the whole workflow digitally, turnaround times for things like repairs and analysis can be cut in half. That means fewer delays on the assembly line and planes getting built way faster.
And this is so important to understand. Zero Defects isn't just some motivational poster on the wall. It's a hard statistical target. Under the Six Sigma standard, it means you're aiming for fewer than 3.4 defects for every 1 million chances for a defect to occur. It is a relentless, data-driven chase for perfection.
And that, right there, is what this is all about. Every rule, every analysis, every piece of tech in this whole unbreakable chain is designed for one ultimate purpose: to make sure that every single time we fly, we are protected by a system that accepts nothing less than perfection.
Which leaves us with a really fascinating question to think about. For decades, that goal of 3.4 defects per million seemed like the absolute pinnacle, the best we could do. But now, with AI that can predict failures before they happen and automation that can remove human error, are we on the verge of a brand new era? Is a future of true, actual zero defects finally within our grasp?